So I'm going to give you talk about flywheels. Many of you might not know much about it. It's a very simple technology, actually, although some parts are not so simple. And I go into the design components. So flywheel is actually a sort of collection of components which make a machine. Brief comparison with other storage technologies, and say a little bit about our gyratricity flywheel, which we've been developing. So a flywheel essentially stores energy by, we have a rotor here, which stores energy. Very simple equation, half I omega squared, but actually the usable energy is not that, because you've got to run, if you've got an electric machine, you've got to run this between a maximum in speed. If you drop your speed right down, and the torque goes, well, eventually to infinity. So we have to run between two speeds. There's a motor generator here which converts the mechanical energy to electrical, which, depending on which way you're going, of course, some power electronics to drive the machine. And this whole thing has to be in a casing for containment, safety. Hold the bearing, of course, there are bearings there, and say more about that a bit later. And really, to make this machine feasible, viable, you've got to get the weight down. There were very extremely heavy flywheels in sort of Victorian times. There's nothing like that. That's what most people think of, but in the Science Museum, and actually it'd be a very compact machine if you do it right. So you've got to get the velocity up. So half mv squared is related to half I omega squared, but in a rotor, because the velocity is proportional to the radius, so that's where your mass is and how fast you spin it. But basically got to spin it fast, means high stresses. How do you do that? Make it safe. You need a vacuum because of these speeds are typically around the speed of sound or even higher. So creating a vacuum isn't particularly a problem. We have vacuums in our CRTs for many years, and we have to vac them down. And in theory, last forever. The rotor will last forever. So there's flywheels that are literally still working in Victorian times. But above all, it must be safe. Of course, we don't want problems there. There's safety issues in any energy storage technology, with fuels, etc., and with fires. So, and again, as we mentioned, when we're looking at characteristics, we need to look at the system mass, the system parameters, not the rotor. Everyone gets fixated on the rotor. It's actually, there's much more to it than that. So going on to the rotor, there are basically three main types. There are developers in all of these fields. The first is sort of solid monolithic steel, so a big cylinder of steel. Don't have a hole in it because that increases the stress. Carbon fibre composites and the laminated steel design. So the solid monolithic, I've tried to be fair here because I'm promoting my solution, but to the upside, single piece rotor is nice and easy. The material is low cost, steel is available. Outgassing is minimal. But the downside is if you get a crack in the rotor, of course eventually this fatigue crack will go right through it and you get through massive chunks. So the solid construction actually promotes that because you get a stress distribution, you get high traxial stress. It's also difficult to check inside the rotor with defects, and also high strength steels. You want a big lump of steel, is very expensive. You're in sort of aerospace, military, if you want very high strength. And really these things have to go in bunkers, or developers that put them underground, and when they go off, there was an accident, actually a very large one. I know it's a good idea to make large flywheels, and it took the roof off and injured people. It's on the internet, but you have to search quite carefully. There's some nice accidents, or not nice accidents. The carbon fibre composite, a lot of interest. This actually got sort of interesting flywheels going in about the sort of 80s, 90s, and they've got their role. The rotor itself is very high energy density. On the theory, you look at the theory, it looks like 10 times better. Actually, you do the sums and you find that that's not the case. It depends on the geometry, where the stresses are. You need a shaft on a composite flywheel. It depends how you design it. It's not just about the material. And one of the benefits is in a failure mode that it disintegrates into kind of powder dust, so it's kind of seen as benign compared to big chunks of material, steel. Problem is the whole list there. Actually, manufacturing is more expensive. You can't get away from that. It's a quite slow process. You've got to take time. You've got there's this explosive failure mode. I don't pretend to understand it, but there's been some unexpected catastrophic accidents where there were some serious injuries, and most of the developers of the composite, they understand this. If you are going to design a composite flywheel, make sure you understand this mode and take steps to contain it because it's not just dust. It's a bit more difficult to check the rotor defects, etc. There's a number of things, but the other thing is it's got to run about over double the speed to a steel flywheel, or certainly the design I'm working on. So the subtle thing is all about the system of the motor generators to run more than twice the speed. The means the power electronics are more expensive because of higher frequencies. The bearings are a bit more difficult. Your windage losses are higher. There's a whole load of challenges, but there are some very good composite flywheels on the market. They're available, and they're actually working very successfully in both in automotive and in grid stability. So this solution, don't claim to have come up with it solely. It's a kind of reinvention of another idea. But if you take the steel and you put it in a layer, laminated, a set of sheets, then if a crack occurs, this crack won't percolate out to the whole flywheel. So you get one laminate fails, and it will fail in a benign manner. You're only capturing it. You have to stop for a small amount. So there's some other interesting. So this doesn't need to go into a bunker. If you're making a sort of certainly grid scale batteries, grid scale flywheel's got to be a reasonable size. Material is low cost, but also you get high strength sheet, very high strength sheet. I mean, relatively, it's not using my raging, but it's a 1200 megapascal steel in stuff that comes off the rolling mill. Well, it's entitled to steel. It's available. You don't have to go to special stuff. Trying to get that sort of strength in a big bar, you'll have a problem. You'll pay a lot of money unless it goes into mass production. Now, the downside is rotor strain. It is more complex. You need an innovative design to get this working, and you need some reasonable economies of scale. So initially it's a bit more expensive, but ultimately it's going to be cheap as chips. That's what I'm trying to do. Some other issues on rotors, and this applies to all of them. You can either have a sort of so you can either have a sort of disc here run at lower speed, or a cylinder. You can't actually have anything really in between because there's a stability issue. But it depends on how you're going to attach your motor generator, geometry, etc. There's also variations of approach. Other questions are, do you go for big flywheels, few of them, or lots of small ones? I prefer the lots of small ones, mass-produced, to solve this problem. Well, like batteries, we don't make massive cells, we make smaller cells, put them together. Makes sense. A bit more difficult to control, but cost of control itself is gone down. It's very cheap actually. Yeah. So a little bit on the detail of the other things. The bearings are very important. There's three main types. I'll get this right. Ball bearings, and used for decades, very robust technology. Passive magnetic and active magnetic. Again, all developers have using these to different levels. And mechanical, nice and simple. They've got a very high overload capability. You have to basically really underload them because to get the life. So in a case of some overload, it's particularly good in vehicles when you might get a shock load. But they need some grease and oil, which can be a disadvantage. There needs to be lubrication. But those exist. They have flywheels in space, so they've got that solved. Not particularly expensive. Requires maintenance, change of oil, etc. So a little bit of maintenance there. Passive magnetic, this is the fantastic solution. You basically don't pay for anything. You just float. We can float the flywheel rotor with one of these in an axial form. Nice and simple, don't pay anything, a very low drag. And unfortunately, you cannot support a rotor, any rotor. It's Earnshaw's theorem that you can't have a stable rotor with these. You've got to have some other form of bearing, which could be a ball bearing or one of these, an active magnetic bearing. So again, active magnetic bearing, great that the friction is very low, no maintenance, but of course you've got to power the system to drive it, the power electronics, this guy here, the box to drive the bearing. And they're actually quite expensive. Part of it is there's not that many developers. We've used this for other projects, and there aren't many. It's not so difficult to do, and but the costs are probably higher than they need to be. It's not the cost of the actual kit, it's really more of a commercial thing. The motor generator, again, three main types. I'm mostly familiar with these. Permanent magnet, switch reluctance, synchronous induction. And they've all got their advantages and disadvantages. Like similarly, we use those for electric vehicles. All three are being tried. So the permanent magnet, highest efficiency, and easier, it's best operating as a generator, but of course you've got a large free running loss, and this is quite important. If you've got a flywheel that's going to be coasting, it depends on the application, this could be very important. If it's cycling all the time, it's less important, the efficiency will be more important. So you've got magnets, and the magnets can demagnetise across. That's similar to electric vehicles, similar issues. Switch reluctance, sort of in between the two, I guess. I mean, you've got the benefit of a solid rotor and you're going with magnets. But there are other issues. I believe the power electronics is a bit more expensive, more difficult, and some rotor loss, so it's getting sort of trade-off. With the induction machine, nice thing about that is it's the type of motor that's most readily available, but we pay a little bit on efficiency, and yes, downside, got larger rotor losses, which one issue that if you try to use one of these in a composite flywheel, you've got one of the problems with the rotor's in a vacuum. You've got to get heat out. So you get heat, this heat goes into the rotor, and that's much more sensitive. If you've got a steel rotor, then we can use one of these machines, so that's a benefit. Moving on to the everyone's seen these kind of plots, rainbow plot, about where these technologies sit, and I sort of agree with most of this. Up here, there's compressed air, sort of large mechanical storage, batteries in the middle here, flywheels here, really competing with supercapacitors. This can actually go up, the actual power level, just like a battery, grid scale battery, make it as big as you want. You have a gigawatt flywheel if you want. Just have more units, so there's no limit to that. But I would say it's definitely on the flywheels that they work well at a very fast, high power, short duration. That's the place. So I did this sort of map here, sort of ticks here, because there's a lot of, you read any of these different reports, they all have different numbers, wildly, orders of magnitude difference in opinion, some based on calculation. Depends what you do. Are you looking at the system? Are you looking at, how do you do it? Are you looking at, power with cycles? How do you mix that? If you drive some system with high power and it only lasts 100 cycles, well, what's the point of that? So you've got to have, again, compare apples with apples. It's difficult. This is my best view. But flywheels offer a lot of benefits in sort of power density, really, the full power response, immediate response, pretty much so. Environmental recyclability, again, this is a major issue. Certainly with an all-steel flywheel, we have that problem. Thermal resilience and life, this is very important. And the fact of knowing your system, as long as the flywheel's spinning, bearings haven't got on it, hasn't blown up, it's not degraded, it's working. So you just need to know the speed pickup, that's all you need, not a complex equation. So it really works well in this sort of high number of cycles, more than 5 a day. It's not every application as this, but certainly more than 5 a day. If you want years of life, you're not going to get this from a battery, but if you have 1 cycle a day, then lithium ion, definitely better. The cycle life, we're talking of more than 20,000 cycles to infinity. I mean, it's very, if you keep the stress down, I mean, the design I've got probably designed for 500,000 cycles. It's that kind of level. But it depends on the application. You have to do the analysis. Certainly, if critical state of health is needed, it's a very good technology. Thermally challenging applications, fast response. So it's actually very good to hybridise this with a lithium-ion battery or with a mechanical storage system to get the best mix, either to defend the life of your battery. You want your battery, you don't want to kill it. I think there's all these major challenges in the APC. You're trying to solve everything at once. Actually, we knock off some of these problems. And so, actually, we want energy density. We want life. That's what we want. We want energy density, but low power. Let the flywheel take all that has the power and all the cycles, and then there are tests actually going on, of course, with hybridized systems, both in transport and in ground power. So a little bit about our flywheel we've got to. So this is a design. We start off with. We had Nissan contact us, contact myself, and said, could you do a flywheel for a heavy SUV? And the sort of application was if you had a hybrid with a small battery, that would not provide the power. A bit like the Prius, if you put your foot down the Prius, the engine has to come on. You can't, the battery will just be. The battery will provide the power, just kill it and be dead in about 3 months. So with the flywheel, you can protect the battery, you can get across town without starting your engine. And that was interesting. It's what, like what most automotive companies put this on, it's sort of on the shelf at the moment, they're thinking about it, they play with all these technologies just in case the law changes or the etc. the drive cycle. So we've got that system working, it's very high C rating, so it's 25 kilowatt. This could absorb the power, so an 8 kilogram rotor in steel, to give you an idea, absorb the energy, braking energy of a heavy SUV from 40, 50 miles an hour down to 0. So it's, you know, it's isn't really the flywheel's not necessarily big and heavy. The key thing with the research project was, what's this thing safe? The hypothesis, was it safe? We took a rotor and in a test rig, we put a big crack in this. We're working with tartar steel, this all the fractional gauge, everything, and we split the thing, made a nice bang in the lab, and we got this sort of nice, I've inherited bunker at City University, blew the whole thing up, and it didn't damage any of the other rotors. There was no kind of cascade failure. It just split. It only scratched the casing. There's lots of sparks. We had a plastic lid. We filmed it with the camera. It didn't even break through the plastic. So it was an amazingly benign failure mode, and that's what's good, because I don't think I want something that will just be contained in the casing. We simulated this to death to find elements of course, and we've got a nice high-speed camera there, do up to 2 million frames a second, and all good fun, and it was holding their breath. There was this almighty bang, and we're going to be doing that again on a much bigger one. That's the next challenge. So, so I'm hurrying through this, so we're doing for time. So the other application, we've got a project on for rail funded by RSSB to look at, first of all, it was a sort of future powertrain competition. How can we significantly reduce fuel consumption? We showed we could reduce fuel consumption in simulations, proper full simulations, by up to 40% for a DMU. And we could do this by, mainly, it's not just the flywheel, actually, energy recovery. We don't need a particularly big flywheel. It's the fact you turn the diesel engine off. You can turn the kind of monster off when you don't want it. The diesel, it just gets this, accelerates the train. The train itself is actually a huge energy storage system. You just coast for about a mile before then you come down to the station. And then you don't have to have your engine running in the station. It's fantastic. Get rid of all these emissions and wonderful things. The problem is it's not actually really funded to the level we need. So we had to do various things there to cut the budget. So we ended up doing a flywheel essentially for the auxiliaries. And the auxiliary power load, actually the energy is similar to the traction load. It's amazing. We learned a lot about this. Now, grid scale battery is a bit of a cartoon. We're just about sort of starting. We actually, only yesterday, we heard we've got a Bayes Energy Entrepreneurs going on. Very happy about that. This is a CAD model of the flywheel, so it's going to be a 5 kilowatt hour. It's about half a ton rotor. Here's some of the discs. And just to give you an idea of the scale, we get rid of the sort of bunkering idea. We put all the flyers like a grid scale battery in here. This is 20 megawatts power, 1 kilowatt hour, so it's the last 3 minutes. This kind of thing, it's something I imagine it could be, partnered with a compressed air storage. Maybe I'll go for even higher power and less time if the response is better. So the utilities are very interested. They can bid for different, they want to stack the revenues from all the different streams. So they want fast response. You've got all your connections, your infrastructure. Somebody, I'd say, to Norway could compete with something like this. It could do everything. So we're just sort of getting into this, and again, this could be even bigger. But if you compare that with this is Beacon Energy, which are sort of pioneers, and this whole thing here is the same power to the one I showed in the diagram. I mean, it's a great system. It's working. So it's flywheel's working. Been running for 6 years. How many? So like 50 cycles a day, in and out, went up and down and down. And but unfortunately, this just shows what happens. One of these went, or two of these went bang. They thought it was an earthquake. I looked at the local news, it's still nowhere. They thought people running out of the houses thought there was an earthquake. Now, if there's no one in there, no one got killed, it was safe. And they say this was a defective flywheel, so I'm not saying this is what's going to happen. I'm saying it may never happen, but if it does, you don't want somebody walking past there. And I'm sure they had an investigation, looked at it, and this other saying there was a steel flywheel went off. It was just huge. What happened there is the bearings went. It wasn't properly bolted down. It went round. It was in a bunker, and it went into the ground, blew soil into the building, and took the roof off. It's absolutely. This is a huge flywheel. I just wouldn't do that. I don't think it's. There are reasons for doing that, but I don't think it's worth it. Just giving you some sort of key attributes, folks, the flywheels, to explain how it works. what the application is. Really, it's not a competitor to batteries. I say it's the friend of batteries. Actually, you can solve leapfrog to these big problems we've got to solve in energy storage. And so it offers this viable alternative, and a little bit out of jar. It's just that's the name of the company. I'm sort of plugging that bit, but this comes out of university research. So we'll see what we get to. Okay.
Thank you very much.